The paper we are breaking down today is Bottom-Up Policy Optimization. Your language model policy secretly contains internal policies.
Right. And for a long time, the standard way to fine-tune these models with reinforcement learning, or RL, was to just treat the whole thing as one giant black box. You look at the final output, that policy, and you optimize it.
Completely ignoring how reasoning actually builds up layer by layer through the whole transformer stack.
Exactly. And the core problem here is that this old approach, it just misses the whole story. So the authors came up with this crucial insight. You can decompose that black box. You can look at what they call internal layer policies and even modular policies.
And that lets you actually see the decision-making as it happens.
It does. And by looking at the uncertainty, the entropy of these internal policies, they found, well, two big things. First, a universal trend. Early layers have really high entropy. They're exploring options. And the top layers have almost zero entropy. They're zeroing in on the answer.
And the second thing?
Critical differences between architectures. Llama series models, for instance, they show this sudden convergence. All the thinking happens right at the very end. But the Qwen series, Qwen 3 in particular, it has this much more human-like, progressive, three-stage pattern. Exploration, then integration, then convergence.
Which, of course, points right to the solution. If reasoning is bottom-up, why not optimize it that way?
Precisely. And that led to bottom-up policy optimization, or BuPO. It's an RL method where you first focus on optimizing an internal layer, say layer 6, before you even touch the final policy.
And the results?
They're really striking. BuPO just did better across all these tough reasoning benchmarks, math, AIME, AMC. It really confirms the whole idea. If you strengthen that foundational reasoning internally, the whole model just gets a massive boost in capacity.
Okay, let's unpack this concept of internal policies, because for anyone who works with transformers, this really changes how you look at that stack. We're used to talking about hidden states. How do you go from a hidden state to a policy?
You have to start with the most important part of the transformer, the residual stream. So if you think about the hidden state, let's call it DILDAR, at any given layer, it's not being completely replaced. It's actually an additive mix of the hidden state from the layer before it and the new output from that layer's modules, the attention and the feed-forward network.
So it's less like passing a baton in a relay race and more like building a composite sketch. Each layer just adds a new detail or a refinement to this growing picture.
That is a fantastic analogy. And because that hidden state $$ is cumulative, the authors realized you could basically grab it at any point in the stack and treat it as the input to generate a token distribution.
So you're treating these intermediate states as if they could be sampled from, as if they were explicit policies.
Yes. Wait, let me make sure I'm clear for everyone listening. This is really different from the traditional logit lens kind of interpretability work.
Right. With the logit lens, you're just peeking at the logits. Here you're saying the cumulative state is a potential policy.
Exactly. The final policy the model gives you, that comes from taking the very last hidden state, $, and running it through the unembedding matrix.
Yeah.
But the insight here is you can take the hidden state from any layer, dollars, that's $, and do the same thing. That gives you the internal layer policy, or the peer layer.
And that captures the model's reasoning capacity right up to that point in the stack.
It does. And then you can go even deeper with the internal modular policy.
Which is where you isolate the individual contributions, right? The attention versus the FFN. That sounds incredibly useful for just diagnosing what's going on.
Oh, it is. You could take just the output from the attention module or just the output from the FFN, $5, and turn those into their own little policy distributions, PSTTN or FFN dollars. And this isn't just a theoretical idea. These become real distributions you can sample from and, more importantly, use as targets for training.
It really peels back the layers of the black box. So when they applied this policy-centric view to models like Llama and Qwen, what did it actually reveal about their different reasoning styles?
The contrast is just fascinating. I mean, you see that universal pattern in all of them. Early layers, high entropy, lots of exploration. Top layers, low entropy, they're converging. But how they get from A to B is totally model-specific.
Okay, let's start with Llama. What does this sudden convergence actually look like?
With the Llama series, based on these octothinker variants they looked at, the model basically keeps its options open. It maintains high entropy for almost the entire stack.
It just holds on to all that uncertainty for a long time.
A very long time. And then, bam, the whole prediction space just collapses in the last 3 layers or so. It's like a student who keeps second-guessing every possibility and only commits to an answer at the very last second.
And what about the FFNs in that process, the part that's supposed to hold the parametric knowledge?
In Llama, the FFNs generally keep adding entropy. They maintain a positive entropy change almost all the way up, which suggests they just keep generating new ideas without much intermediate consolidation. It works, but it relies on this massive, sudden contraction at the end.
Which sounds, I don't know, a bit brittle maybe, compared to a more structured approach. So how does Qwen handle it?
Qwen, and Qwen 3 especially, is what they call the progressive reasoner. It's a much smoother, more gradual reduction of uncertainty layer by layer. They measure this using what they call the internal entropy change, or delta H dilla.
So if delta H dilla is positive, the layer is adding possibilities, and if it's negative, it's narrowing them down.
You got it. And in Qwen 3's FFNs, they found this really clear three-stage pattern. They call it the EIAC pattern: exploration, integration, and convergence. It's this progressive structure that makes it so interesting.
Let's drill down on that. For a model like Qwen 3.4b, where do these stages actually map onto the layers?
Okay, so in the Qwen 3.4b model, the lower layers, let's say layers 1 through 6, they show a positive delta HFFFN. That's the exploration phase. The FFN is actively expanding the search space.
It's brainstorming.
It's brainstorming, exactly. Then, from about layer 7 all the way to 26, delta HFFN is basically 0. This is the integration stage. The model is just calmly retrieving and reusing its stored knowledge. It's consolidating the facts it needs.
So it's pulling in the right information without adding a bunch of new noise or confusion.
Yes. And finally, in those top layers, say 27 to 36, delta HFFN goes negative. That's the convergence phase, where it collapses all that information down toward the final answer. It's a pattern that feels a lot more like how a person might solve a problem.
And just to confirm, the modular policy analysis showed it was the FFN driving this whole staged process in Qwen, right? What was attention doing?
That's the key. The FFN is steering the consolidation. The attention module, meanwhile, generally keeps a positive entropy change. Its job is to keep pulling in new contextual information, sustaining that expansion throughout the process.
It's a clear separation of duties. FFNs consolidate. Attention explores context. And this clear structure seems, well, like a perfect target for optimization.
It is. Which is where we move from just observing this to actually intervening. If the theory is that reasoning builds from the bottom up, then the obvious experiment is to try optimizing from the bottom layers first.
So how do they test that hypothesis?
Well, they needed a way to aim their RL algorithm at a specific internal layer. So they adapted a method called GRPO into something they call inter-GRPO, intermediate GRPO. All it does really is change the training objective. Instead of targeting the final output there, it targets an internal policy, K-layer light.
And they ran this on Qwen 3.4b, right? I think they picked 3 different layers. Layer 6, the exploration one, layer 26, the integration one, and layer 35, almost at the end. What happened when they just optimized those internal layers by themselves?
Optimizing only an internal policy. It caused performance to collapse pretty fast, but the interesting part was how it collapsed. When they targeted the late layer, layer 35, the model's outputs became unstable, really long, and repetitive. You're basically breaking the final decision-making.
And the middle layer, 26.
That one showed really unstable entropy that just kept climbing.
Which feels like you're sending mixed signals. You're telling the model to consolidate facts, but also to keep exploring. It gets confused about where it is in the reasoning chain.
That's a great way of putting it. But when they optimized the low layer, layer 6, it was much more stable. The entropy grew in a controlled way. The response length stayed normal. And this led them straight to what they call the feature refinement phenomenon.
Okay, this sounds like the real core of it. What exactly is feature refinement here?
So when they applied a moderate amount of optimization to layer 6, something incredible happened. The hidden state representations at layer 6, which they call 6NE66, suddenly became way more similar to the final layer's representations, HE's dollars.
Wait, so the bottom layer started to learn what the top layer was thinking?
In a sense, yes. It was forced to capture high-level semantic information much, much earlier than it normally would. You're essentially forcing the bottom layer to build a better foundation.
It's like you're not just tweaking the weights. You're fundamentally upgrading the quality of information that foundational layer carries. Like forcing the primer coat of paint to already have the detail of the final artwork?
That is the perfect analogy. The optimization makes layer 6 build this more robust, higher fidelity representation. And once you have a better launchpad, the next 30 layers have a much better starting point for everything they do.
And that's why moderate optimization was the key, I assume. If you push too hard on layer 6, you just make it converge too early.
Exactly. That's the trade-off. Too much alignment, and you destroy the natural progression. You hurt performance. Your perplexity goes up. You need just enough of a warm-up at the bottom to refine those features without killing the exploration space.
Which brings us right to the full BPO algorithm. This is the intervention based on all that diagnostic work.
Right, so BPO is just a two-phase process. In phase one, for a certain number of steps, you train the model using inter-GRPO. You're focused entirely on optimizing that internal layer policy.
Yeah. And you don't just pick that layer randomly. It's based on that entropy analysis you mentioned earlier.
Correct. You pick layer dollars to be the last FFN layer that's still in that positive exploration phase. For the Qwen 3 models, that was layer 6. So you're making sure you optimize the foundational features, not the integration or convergence ones.
So after you've established that stronger foundation, what happens in phase 2?
After that initial period, the training just switches back to standard GRPO. You go back to optimizing the overall final policy. But now, that final alignment benefits from the much better internal representations you build during the warm-up.
Let's talk results. Because we're talking about really complex math problems here where tiny differences in reasoning can lead to huge performance gaps. How did BPO stack up against the baselines?
The gains were really substantial. I mean, it completely validated the approach. For the Qwen 3-4B model, it gained over 4 points on the AMC math benchmark and nearly 4.7 points on AIME 24, compared to just using standard GRPO. And these aren't small bumps. A 4-point gain on these tasks is a huge leap in how reliable the model is.
And it wasn't just for the nicely structured Qwen models. It also helped Llama, which has that, abrupt convergence pattern.
It helped Llama a lot, yeah. It improved one of the Llama OctoThinker models by over 3.6 points on average. And the training dynamics show you why. Llama models tend to start with a more constrained exploration space. That initial bottom alignment phase in BPO basically forces them to broaden their horizons, giving them a much better foundation to work from.
They also looked at the pass at K metric, which I think is important. For anyone listening, pass at K is your accuracy if you let the model generate K different answers and check if any of them are right. Why does doing well across a wide range of K values matter so much?
It's crucial because it shows you're improving the model's fundamental capacity, not just getting it to spit out the single most likely correct answer more often. If DBPOs are better at pass at 16, pass at 72, all the way up to pass at 256, it means the model's entire distribution of possible answers has gotten better. It's just generating higher quality thoughts more often.
So the consistent improvement across all these metrics really drives home the point. Being aware of the layers, understanding the progressive nature of reasoning in these models is incredibly effective.
Absolutely. And that decomposition into internal policies is the key that unlocks it all. It lets you see these architectural fingerprints, Llama's abruptness versus Qwen's staged EIC pattern. And it shows that a bit of moderate bottom-up optimization can fundamentally rebuild and strengthen a model's reasoning ability.
Before we wrap, we should probably touch on the limitations the authors themselves pointed out, because that's where the next wave of research is going to go.
For sure. I mean, this analysis was mostly on Qwen and Llama. We have no idea if MOE models or models with different architectures behave the same way internally. And importantly, picking the right target layer, Bellers and the right number of training steps, that's all totally model dependent.
Which sounds like a bit of a tuning headache for anyone trying to implement this. Every time you get a new base model, you have to run this whole entropy analysis to find its layer 6, and then tune the number of warm-up steps.
It is a tuning headache, but it also points to something much bigger. If certain parts of the model, like the FFNs in Qwen, are reliably responsible for these distinct, almost human-like stages of reasoning, exploration, integration, convergence, it raises a really provocative question about how we design these models in the first place.
Right. If RL can only enhance these structures after the fact, after all that expensive pre-training is done, what could we do differently in the architecture or the pre-training itself to build in these mechanisms from the start? Could you actually engineer a model to be a more structured, progressive reasoner right out of the box, and maybe reduce the need for all this complex model-specific tuning down the line? You'd be shifting the focus from just optimizing the final output to optimizing the cognitive architecture itself.